Okay, hello everybody. So today we have it's our honor to have invited this training who is coming from Peking University of Hong Kong. So the training have did a bachelor in the Duke University, and afterwards he become a PhD student in Harvard University under the advisor Mark Thiessen. And afterwards he did a postdoc at the University of Wisconsin Madison, and now he is a assistant professor in at the University of Hong Kong, and today he's going to give us a talk on Picard jobs for non-ordinary K3 surfaces. So let's welcome him.
Thank you very much for the invitation. It's a great pleasure to speak here. So the work I'm going to talk about today is all joint work with Ruofan Jiang and Anand Shankar. Okay, so since this is a colloquium talk, let me start with something very classical. This is a question that can be considered by the ancient Italian school of algebraic geometers. So say you take a surface in P3, which is given by some homogeneous polynomial in 4 variables. How to find curves on the surface? So the most naive thing you can do is to write down another surface in P3 and then take the intersection with your original surface. So there I drew a picture on your X intersecting another H. And then the resulting curve is by definition a complete intersection curve in P3. So here's a general theorem due to Noether and Lefschetz. So you can ask the question whether these are all the curves you can find on your surface X. And it turns out that this is true for a very general surface. So, well, of degree at least 4. So in that case, the restriction map from the Picard group of P3 to the Picard group of your surface is an isomorphism. And if you think about, okay, you can think about elements of your Picard group as line bundles. In that case, you just restrict your line bundles to your surface. Or you can think of it as a divisor. So if the divisor class is given by a hypersurface H, then you just take the corresponding intersection with X and take the divisor class of the resulting curve. So the fact that this is an isomorphism means that for a very general surface of degree 4 or higher, every curve is given by taking complete intersection with another surface. So there are no more curves. Yeah. So the brief history of this is that Noether already considered this problem and had in mind a way of how to do this, but her argument wasn't completely rigorous. And then Lefschetz revisited this problem. And along the way, he discovered his famous Lefschetz-Bellman theorem, which I'm going to mention later, and give a complete, rigorous proof of this fact. But of course, this is only true for a very general surface. There are certainly exceptions to the conclusion. But these exceptions, they form a union of proper subrealities. In fact, this was a key insight of Noether. And the locus of those surfaces with more curves than just the complete intersection curves is known as the Noether-Lefschetz locus. All right. So here's a concrete example for an exception. Say you take the Fermat quartic in P3, and then consider the line given by the equations written out there, using a 4th root of -1. Then this line completely lies on X. But we know that by Beziou's theorem, any complete intersection curve on a quartic surface will have to have a degree being a multiple of 4, because your original surface has degree 4. So that implies that the line you find cannot be given by taking complete intersection with another hypersurface, because it has degree 1. So this implies that the rank of the Picard group of X is strictly bigger than 1. There's 1 coming from the polarization, but there's more. So more generally, given a smooth proper family of varieties, we can define the Noether-Lefschetz locus to be the locus on the base where the geometric fibers acquire more divisors or line bundles than the geometric generic fiber. So usually we just say that this is the locus where the Nernst-Severi group drops. And the Nernst-Severi group is, of course, the Picard group modulo homological equivalence. Like, or algebraic equivalence. So now let's ask a further question. So in that Noether-Lefschetz theorem, can you replace the word very general by general? So very general means you're allowed to throw away countably many, but possibly infinite many closed subvarieties on the base. General means you're only allowed to throw away finitely many. It turns out that the answer is no. And this question, so when you consider an arbitrary base field, including those of positive characteristic, this was addressed by a paper by Siliberto, Harris, and Miranda in the late 80s. But over C, this can be seen quite explicitly by considering classical Hodge theory. So the main tool here is the so-called Lefschetz-Ziquan theorem. So if you take a smooth projective variety over the complex numbers, the Nernst-Severi group, well, more precisely, the Nernst-Severi group modulo torsion, which I'm ignoring here, is given by taking the intersection of the second Betti cohomology with integral coefficients with H1 omega x. And this intersection is taken inside the de Rham cohomology. So here, let me briefly recall the basic statements of Hodge theory. So we know that the de Rham cohomology, okay, actually, this works for any n. There's a canonical isomorphism to the Betti cohomology tensor with C. And on the other hand, that there's a decomposition, a Hodge decomposition. Given such. And usually we write this subspace as H upper J. Let me write J here. And this is H upper IJ. Okay, so in particular, my H upper 1 is a subspace of H upper 2 de Rham over C. So inside a complex vector space, I'm intersecting an integral lattice with a subspace. All right. So now, as your variety varies in a family, the integral lattice given by Betti cohomology remains rigid, analytic locally, and it is just given by parallel transport. But the complex subspace given by H upper 1 varies continuously. So from the point of view of Lefschetz-Ziquan theorem, the Noether-Lefschetz locus is exactly the locus where your subspace contains an extra lattice point. Okay, so here's a picture for what is going on. I said that this is a cartoon because this actually violates a Hodge symmetry, so it doesn't really happen, but let's pretend that this is a picture. So let's say that your H upper 2 with R coefficient is given by a plane R2, and the integral cohomology is some integral lattice. And your H-1, being a complex of vector space, is actually defined over the real numbers. And it descends, its real model is given by taking intersection with H-2R. And let's imagine that this is some line passing through the origin. So locally, as you vary your x, the lattice stays the same. And your line L will rotate continuously. So then the question is, when does L intersect the lattice? And from the picture, it is clear that, well, the answer is precisely when your gradient is a rational number. And this is where you acquire a new divisor. So from the picture, you can see that in this case, the Noether-Lefschetz locus is going to be analytically dense, not just Zariski dense, analytically dense, in the same way that rational numbers are dense in real numbers. Okay. All right. So this cartoon can be made precise by considering the variations of Hot structures for an actual family over C. So infinitesimally, the variation of Hot structures is captured by the Kodaira-Spencer map. Okay, so once you have the variations of Hot structures, you can write down this map. But let me give a more concrete geometric description of this map. Okay, so you take, well, this is the tangent space of your base. You can first map to H of a tangent bundle, because this is given by a deformation of the variety to the dual numbers, which are classified by this space. And then you take the cut product. So now suppose you're given an element in H-1, well, H-1 omega x. You take the cut product of this and this, and then you land in H-2 OX. So the Kodaira-Spencer map there is given by the composition. But this makes sense as long as you have variations of Hot structures. So this map remembers infinitesimally how your Hot structure varies. And there's a theorem by Green, which says that if for some lambda in V11, the resulting map from the Kodaira-Spencer, from the tangent space to H-02 is surjective, then the Noether-Lefschetz locus is analytically dense. Okay, so let me give an explanation for this hypothesis. So if you look at our cartoon, and you can ask, okay, so now what happens if we're in a higher dimensional vector space? Let's say instead of R2, you have R5, and your L is 3-dimensional. Okay, you have a 3-dimensional subspace in a 5-dimensional space. Then you need to rotate your subspace in 2 directions to swipe out an open subset of the total space. So the hypothesis here in Green's theorem is basically saying that you are rotating your subspace in enough directions to make sure that you swipe out open subset of the ambient space. So now if you look at the surfaces in P3, there is a generic Toretti theorem, meaning that this map is injected for a surface in P3, and when your base is a modular space. So then you can quickly check that using Green theorem, you know that the neutral-Lefschetz locus is analytically dense.
That's a good question. So
yes.
Did you say what makes this match suggest? And the theorem is saying which is subjective, but did you just say any condition that can make this match subjective?
That's a good question. Okay, it takes some explanation. All right. So now let's look at a simple case of the theorem. So this is a case when your H upper 02 is equal to 1. And the most concrete example is a case for K3 surfaces. In this case, the hypothesis of Green theorem just amounts to saying that your variations of Hot structures is non-isotrivial. So this means your VHS cannot be trivialized after passing to any top cover of the base. Seems that, oh, wait. Okay. So this special case about K3 surfaces was also observed by Okuisu. Okay, so now let's ask the following question. What happens if we replace the base S by an arithmetic curve? So before S was some complex variety, and in the case for K3s, you can take S to be a complex curve. But now we want to consider an arithmetic curve. So let's say S is the ring of integers of some number field K. So in this case, probably the first result in this direction is the theorem of Charles, which was published around 2018. So the theorem says that suppose you take two elliptic curves, E and E prime over K. Of course, then you need to spread out your curve to an open part of the ring of integers. Then there are infinitely many primes on the base, such that your elliptic curves become geometrically isogenous modulo P. So geometrically isogenous means they're isogenous after base change to the algebraic closure of the residual field.
What's the isogenous?
Isogenous means that okay, so E okay, so an isogeny is a map between elliptic curves for general abelian varieties, is a map of finite kernel. Since in this case your source and target are both proper and have the same dimension, then in fact it has to be surject and the kernel is. So okay, now on face value, this is not a statement about the neutral-Lefschetz locus, but here's a fact: when you take two elliptic curves and take the product, you get an abelian surface. Then the Nernst-Savary group of the resulting abelian surface is given by two copies of Z plus the home between E and E prime. So that means in a family, if you have an extra homomorphism from E to E prime, then you have an extra line bundle on the product of the two curves. So Shell's theorem implies that if you consider the product of a Beating surface, then the Noether-Lefschetz locus, which is a sublocus on the ring of integers, is infinite or dense, because now you're over a curve.
I got a question. So
yes.
In the last line, when you recall something that is equal, not isomorphic, do you really mean they're canonical?
They're canonically isomorphic.
Okay.
Okay. So
what is an act?
Well, so you have a copy of Z2 because you have E, the first factor times a point, the second factor times a point, and now you take an element in home, take the graph. That gives you a divisor on the surface. So this is a completely canonical asymptote.
So in Charles' theorem, there's no relation between E and E prime, arbitrary.
Yes. So in fact, if your E and E prime are CM, then this is already known. Because if you're CM, then we know that for half of the primes, you have supersingular reduction, and the supersingular elliptic curves are always isosceles. So yeah.
So the point that I feel a little bit uncomfortable because on the left hand side of the equation there is symmetric, like E and E prime, right?
Yes.
On the right hand side, the home make it home E prime. You couldn't switch that. So just yeah, that's why I feel a little bit confused. How this could be a canonical?
Well, the actual formula for general Beating varieties would be involving E. So you have a term like home A to B dual.
I like that.
Okay. But these are elliptic curves, so they are.
Okay. Self-dual.
Yes, they're self-dual. I'm implicitly using that. Okay. Okay. And in the previous example, you can also take the Kummer construction of the Beating surface and obtain a K3. So this is also a statement about a particular type of K3 surfaces. And then this can be generalized to all K3s over a number field. So at first there was a theorem by Arun Shankar, Arnott Shankar, Yunqing Tang, and Salim Tayu, which assumed that X has full reduction everywhere. But then there was a paper by Tayu alone, which removed this full reduction hypothesis. So now that this is just true for any K3 over a number field. Then the conclusion is still that for infinite many primes, okay, you need to spread out your X, of course. Then the multi-P reduction acquires more divisors. Okay, so here's an elementary observation. If the rank of your Nernst-Savary group over K bar is odd, then then you have a jump in Nernst-Savary modulo every prime due to the Weil and Tate conjectures. Okay, this is because when you consider a K3 over the algebraic closure of a finite field, it always has even Picard rank. Because the Frobenius eigenvalues, which are not roots of unity, always come in pairs by the Weil conjecture. If alpha is a Frobenius eigenvalue, then alpha inverse is also a Frobenius eigenvalue. So if alpha is not a root of unity, then so is alpha inverse. So they always come in pair. But the second big number of a K3 surface is 22. It's also an even number. So the Frobenius eigenvalues, which are roots of unity, are also, but they're also an even number. So if you apply the Tate conjecture, this implies that the Nernst-Savary group at Zariski closure has even rank. So this little observation was actually very useful. It was used in a sequence of works by Bogomolov, Hassett Schinkel, Lee Liedtke, and Chen Cornelis Liedtke that resolved the following conjecture of Mumford. Namely, every K3 surface over the complex numbers has infinitely many rational curves. So it's quite amazing that you have some hard facts in characteristic P, and you deduce something in you deduce something over C. All right.
But
yeah.
How do you see this pair is distinct?
How do you see
in this alpha and alpha and both are distinct? So
because let's say if alpha is not the root of unity, so then right, because if they're equal, then alpha squared is then alpha is minus 1. Okay, so now let's consider the case when your base S is a curve C over a finite field. And then there's a theorem by Modic, Shankar, and Tang, and in the Gould reduction case, and also tell you in the value reduction case, which says the following: if you take a non-isotrivial family of K3s over C, which is generically ordinary, then the Noether-Lefschetz locus is dense or infinite because you're over a curve. So let me briefly recall what the word ordinary means. So for abelian varieties, the word ordinary can be explained by the torsion points. So say you take a genus G abelian variety, dimension G abelian variety, and over some base field K. If your characteristic is 0, then the group of n torsion point over K bar is always isomorphic to Z mod NZ up to rank 2G. But if you're in characteristic P and you ask for P torsion point, then you're ordinary if and only if you're isomorphic to Z mod PZ to the rank G. And this is already the maximal P rank you can have. So note that in calculus 0 you have 2G, and in calculus P you have G. So yeah, sorry. So in characteristic P, you can think of the ordinary varieties as the least pathological cases compared to their counterparts in C. And these varieties will behave very much like their counterparts over C. So here I use the word pathological if you think of what happens over C as being natural. But if you do calculus P stuff every day, you think of these things as features, not pathologies. So it's a matter of taste.
Let's see about the counterparts.
So
parts theory.
No, I just mean that if you consider abelian varieties in characteristic P, then you compare with abelian varieties over C, and yeah, it's not a very rigorous statement.
But if you have some spread out of the ordinary abelian variety and reduction P, then this always is ordinary.
That's a good question. Sorry, your question is if you take an abelian variety over C and spread it out and reduce modulo P, is it always ordinary? That's not true. Although in some cases we conjecture that is true for most of the primes, or at least a positive density of the primes. But certainly there are primes where your reduction is not. So okay, one way to see this is that the moduli AG is flat over Z. In fact, it's smooth over Z. So any characteristic P point can be lifted to characteristic 0. But it is true that in history, when the lifting result was first proved, it was proved by first deforming a general variety to an ordinary variety, and then deformed to calculus of 0. So there is some. It is a very relevant consideration. So for elliptic curves, this can be seen more concretely by counting points. You take an elliptic curve over FQ, then the number of directional points is always given by Q plus 1 minus some correction term. And this correction term is a trace of Frobenius. And I call it a correction term because by a famous result of Hasse, we know that its order is less than 2 times the square root of Q. So it's, right? So it's a smaller order to Q. But then you can distinguish whether E is ordinary or supersingular by looking at whether this correction term is divisible by P or not. I mean, it's always an integer, so we can ask whether it is divisible by P. So if you're familiar with this kind of thing, you know that another way to say this, for elliptic curves, you know that the formal group of your elliptic curve is the formal torus if you're ordinary, and it has height 2 if you're supersingular. So we can extend this to the case of K3 surfaces. Now you take a K3 over, in characteristic P, and let height be the formal Brouwer group. So this is some analog of the formal group of an elliptic curve. So if your height is finite, then this height can also be characterized by the number of Frobenius eigenvalues of p-adic valuation less than 1. If your height is infinite, or in the supersingular case, then all Frobenius eigenvalues have p-adic valuation 1. In fact, in that case, the Frobenius eigenvalues are all roots of unity in the supersingular case. Okay. So now let's ask the question, but what happens in the previous theorem? Your family is not generically ordinary. And here's a counterexample, which was remarked by Maulik, Shankar, and Tang. So again, let's consider a product abelian surface given by taking the product of 2 elliptic curves. Except that for one of them, let's take a constant supersingular curve. And for the other, let's take a non-isotrivial family of elliptic curves. And then, well, here the product should be taken over the base, not an absolute product. So then we know by the formula I wrote before, the Narasavari of the product is Z2 plus hom E prime. So the Picard rank jumps precisely when the specialization of your first factor becomes isogenous to the constant elliptic curve of your second factor. And this is equivalent to saying that you want your ES to be supersingular because supersingular elliptic curves are always isogenous to each other, and vice versa. But then we know that in a non-isotrivial family of elliptic curves, there are at most finitely many supersingular fibers. So this implies that the Noether-Lafschatz locus for this family is finite, and in particular not Zariski dense. So the goal of the theorem that I'm introducing today is precisely to understand exactly what is going on. What fails in this counterexample that compared to to the generic ordinary case. So roughly speaking, the problem is that this example is too close to being supersingular. So you can think of the supersingular case as a case of whatever goes wrong in characteristic P does go wrong. It is the antithesis of being ordinary. So for one thing, a supersingular elliptic curve, K3 surface has Picard rank 22, which is equal to the second Betti number. And we know that it is not possible over C, because over C, you have the Hawkes decomposition. And you can only find the line bundles here. So over C, your Picard rank is at most 20. But in the supersingular case, you can reach up to rank 22. Moreover, a supersingular K3 can be unirational. In fact, it was conjectured by Shiota that they're all unirational. This is, again, not possible over the complex numbers. Okay. So to introduce the statement of theorem, I need to introduce I need to parameterize my K3 by some orthogonal Schmal variety. And let's say we take the smallest one containing the image of the curve. And here L is a suitable lattice of signature 2D. This lattice L is essentially the Nernst-Savary lattice of the geometric generic fiber of your family. So the multiple reduction of your Schmal variety has a Newton or Height stratification. So here I'm assuming that P is prime to the discriminant of L, and I'm ignoring these technical assumptions. We say that your family is exceptional, either if it is a supersingular or it is almost supersingular, meaning that C is contained in the smallest non-supersingular locus on the Schmal variety, and your lattice L becomes a bunch of copies of the hyperbolic plane at Zp. So unless you're already familiar with orthogonal Schmal varieties, this probably doesn't mean much to you. But I'll say how it comes up. Okay, so finally, this is the main theorem. If you take a non-isotrivial family, which is not exceptional, and also satisfies a condition that the connected étale exact sequence of the enlarged Formal-Brouwer group of the generic fiber is not split, then the Noether-Laplace locus is dense. So here the enlarged Formal-Brouwer group is always a Petersson group. Over a perfect field, the connected étale exact sequence always split. But here I'm taking the generic fiber. And the generic fiber, we're taking something like FQ printed as T, so it's not a perfect field. So then it becomes a highly non-trivial condition to ask for this Petersson group to split. So in this theorem, the condition of being not exceptional is trying to exclude the most obvious obstruction from frobenius for the statement to be true. And by the most obvious obstruction, I mean, if you're in a situation in which your Picard rank can only jump at supersingular points, then of course you cannot be dense. So this is what I call the obvious obstruction. And it is precisely captured by this very technical condition on the last line. But beyond that, we also need a condition star, which can be viewed as saying that the crystalline monodromy group of your family is not too degenerate. So you can think of this as some condition on the. You can think of star as some condition on monodromy. And moreover, this condition is automatically satisfied if your family is generically ordinary. Basically, it's because in the ordinary case, it just follows from the fact that a formal torus is completely rigid. It does not deform at all. So in particular, this theorem will subsume the previous theorem of the generic ordinary case. Okay, so now let me say a word on the core strategy of proving things like this. The main point is to intersect your arithmetic curve with a family of special divisors indexed by M on your target Schmal variety. So what is Zn? It is a special divisor that parameterizes points where the fibers acquire an additional divisor of degree M. By degree, I mean the self-intersection number. Yeah. In fact, if you view it, if you take the point of view of a Schmal variety, I should say, take the self-intersection number of some special endomorphisms of some Fuka-Sasaki abelian varieties, but let me not use that language. So now you put all these divisors together into something like this. So here Q is some formal variable. Then this gives you a modular form. So then you can use Borch's theory to control the intersection number of C of your curve with the special divisors. Well, you can estimate the growth rate of the Fourier coefficients, and this will tell you that this global intersection number grows at a rate of m to the exponent b plus 2 minus over 2.
But why this becomes modular?
This is some deep theorem by a lot of people. Right. Yeah. So now let's take a point P on the curve. We want to bound the local intersection multiplicity of the curve with a special divisor at P. And this is primarily done by deformation theory. So there's two things you need to count. First, you need to know how many divisors of degree m there are, and this can be controlled by the Ziquan mass formula for quadratic forms. And then for each of these line bundles, you need to know how far they can deform along your curve, and this is done by deformation theory. And this is also the
But in this case, the intersection, the dimensional intersection may not be zero.
Sorry?
The intersection of C with Cn,
Yes.
its dimension may not be zero. And how can you define the intersection with this?
Oh, if it's zero, then it's just zero. If they do not intersect.
No, I mean, if dimension is zero, then intersection will fix to be well defined. Otherwise, you may need to consider local characteristic in general category.
I don't understand. I mean, I'm intersecting a curve with a hypersurface, with a divisor.
Okay.
Right. So,
okay.
So, yeah.
But what happened in C is contained in this divisor, I mean, not transversely.
That's a great question. So that's why at the beginning we need to take the smallest Shimura that contains C. So then by definition we exclude the situation when C is contained in some Z.
And I have another simple question. So what is C? Arithmetic curve.
So my setup is that I have some.
You consider zero intersection.
So the setup of the theorem is that I have a family of K3s over C, right? And I have a classifying map from C to the Schmal reaction. So let us pretend that this is a closed embedding, and I view this curve as literally a curve on Schmal. And then I have these divisors and Ziquan. And then I'm intersecting this curve with divisor. Okay. So if your P is not super singular, then the growth rate, this local growth rate, is strictly smaller than the global growth rate. So then you know that there has to be infinitely many such points if every intersection point is not super singular. But if you are super singular, then the local intersection multiplicity does indeed grow on the same order as the global intersection number. So this allows for the possibility of having only finitely many intersection points. And as we have seen, this indeed happens for some families. So this means we have to have very precise control on the constants appearing in this asymptotic sign. And this is also the hardest part of the proof. In fact, this general strategy has already been used in the previous work by Morik, Shankar, and Tang. And it was already very hard over there. But in the non-ordinary case, this step becomes even harder because, this can also be seen from the statement of the theorem, because if you're not careful, you can easily prove something wrong. Because there are these counterexamples which stand as test cases. So what plays an important role is the tangency of C with each of the Newton stratum of your Schmal rarity. So a Newton stratum is iteratively cut out by some generalized form of Hessian invariant. These are some global functions on your Schmal rarity. You consider the order of vanishing of these functions at your point of interest, and you keep track of the order of vanishing, and then you do some huge combinatorics to control this. So this last line is actually the main point of the paper, but I don't want to go too deep into that. Okay, now let's zoom out from the characteristic P case and compare it with the case over C. So you can tell that the argument in characteristic P looks nothing like the characteristic zero argument. In characteristic zero, you just deform some hyperplane in a fixed space, and you can already see the answer. Moreover, over C, your argument is completely analytic local. But in characteristic P, you have to have very global considerations. You need to put all special divisors together. You need to know their growth rate, etc., etc. But still, we want to see some parallel between the situation in characteristic P and the situation over C. So over C, there is a lot of recent progress on the following question. And a lot of people like Klinger, Otmanovska, Baldi, Umo, Urbanik, Khalifa, Tayu, Porozen. And this is an incomplete list because in the interest of space. But the question is, given a polarizable VHS, when is the Hodge locus? In other words, the locus where you have extra Hodge tensors, or certain part of it, dense. So if you look at general theorems that guarantees density for a Hodge locus, there are usually two types of conditions that goes into the hypothesis of such theorems. So first, you need to ensure that the expected dimension of the locus you're asking for is non-negative. And this is the most important part. And this condition is related to what I said about this picture. I mean, in general, your subspace needs to deform in enough directions to swipe out an open part of your ambient space. And this expected dimension statement is a formal way of saying what I just said. And secondly, there is some condition which says that the monodromy group, in some suitable sense, it cannot be too degenerate. So now when you take a weight 2 variations of hot structures, say coming from the second cohomology of surfaces, and let's say your hot number h upper to 0 is equal to 1, then it turns out that these two conditions coincide. They are both equivalent to saying that your BHS is non-isotrivial. And this is because if you have a BHS, well, this is essentially a consequence of the theorem of the fixed part. If your monodromy is trivial, then you cannot have a non-trivial variation of hot structures. But these two conditions become separate in characteristic P. For example, you can take the locus of supersingular field breeze, and on that locus, your monodromy becomes trivial. I mean, it's a priori finite, but you can pass to some Ital cover. But they have non-zero Kodaira-Spencer map. So the rank of the generic Kodaira-Spencer map is the same as the dimension of the pure image. So this is also this is another way of saying why the supersingular case is so special, and it also gives you a heuristic on why in characteristic P we want to gauge how far you are from being supersingular. Okay. So finally, I want to say the general theme of the kind of questions we're studying. So in general, we wish to understand the distribution of divisors, or more generally, algebraic cycles in a family of varieties. And oversee, a lot is known by studying variations of hot structures. So in the past decade, there has been lots of very exciting developments on this side. So in characteristic P, we believe that the ordinary varieties should behave pretty much like the case over C, at least in a Schmorr setting. I mean, for varieties parameterized by Schmorr varieties. And there is an AIM conjecture, which tries to make this statement precise. So it's called the AIM conjecture because it was made during a workshop at the American Institute of Math. And the conjecture says the following: take S to be a Schmorr variety, and I'm taking it into a model, and let's say it is hot type, etc., etc. And let's say you take two subvarieties in its mod P fiber, and such that they are both generically ordinary. And we want to consider the intersection of X with the union of all Ty, where T runs through the Hecke operators. In other words, we're taking the intersection of X with all the Hecke translate of Y, and the conjecture says that this is this. in X. So over C, the analog of such statements can be is proved by Taiyu and Torothan, which I mentioned up there. And we believe that if both of the varieties are generic or ordinary, then the same should be true. But in the non-ordinary case, much less is known. So to be fair, even in the ordinary case, very little is known about this general conjecture. But the thing of the non-ordinary case is that it's not even super clear to us how to make a conjecture. But on the other hand, we do want to understand exactly how the Frobenius, which you don't see in calculus 0, constrains the distribution of cycles in calculus P. Or in a Shimura setting, constrains the Hecke orbits of a subarray. So there, but there are two related works regarding this this question. So in the interest of time, I didn't spell out their exact theorems. But there's a recent paper by Marco Diazio and Paul van Hoften, which proves the full Hecke orbit conjecture. So the conjecture is about the case when you take your X. So let me write HO conjecture. You take your X to be the Shimura variety itself, and you take Y to be a point. Sorry. There's one key thing which I forgot to mention. You need to assume that X and Y are of complementary dimension. Otherwise, what I said is not. Okay. So in the extreme case, you take one to be the ambient space, the other to be a point. And then the full Hecke orbit conjecture says that the Hecke orbit of Y, which is a point, is dense in the central leaf containing it. So the central leaf is some refinement of the Newton stratification, if you like. So that gives us something on what to expect in a non-ordinary case. And then there is Ruofan Jiang's work, who is also a collaborator. So he has a previous paper which proves the following about almost ordinary abelian surfaces. So almost ordinary again means that it's not ordinary but closest to being ordinary. If you have an almost ordinary abelian surface whose endomorphism, global endomorphism ring is Z, then there are infinitely many points where your specialization is isogenousous to a product of elliptic curves. So this can also be phrased as as intersecting a curve and certain special a subclass of special divisors. How to say this? Intersecting a curve in an orthogonal Shimura variety with a Hecke translate of some particular special divisor. Yeah, so these are probably the only known examples of what we know in the non-ordinary case.
So then, just ordinary cases like Tom,
Yes, Tang. All right, so that's the end of my talk. Thank you very much for that. Yes.
Is there similar conjecture in other Shimura varieties?
That's a good question. I think for other Shimura varieties, it will be much more complicated because the orthogonal Shimura variety is particularly simple in that, at least for the non-super singular part, your every Newton stratum is a central leaf. And this simplifies things a lot. In general, you see, in general, locally, your Newton stratum will be a product of the central leaf and something called an isogenous leaf. And we do not know what to conjecture in that case.
이거는 Ziquan modular varieties.
In what?
Ziquan modular varieties.
Zero. Yeah.
Ziquan modular varieties.
You mean AG? Or yes.
So,
The case for AG is very complicated. We do know the case of unitary Shimura variety. The unitary case and the orthogonal case are very similar for the reasons I said. But Zigo is very hard.
Is there any reason why you expect this Hecke orbit will be dense in these contexts? This AA and AIM. Why do you?
Well, I guess I wasn't in that workshop, so I didn't know what they were thinking about. But I would guess that their intuition is that this is true over C, and in the ordinary case, things should behave like C. Yeah.
Is the Hecke this person this still testing Hachirokusu?
Say that again?
Is the Hecke orbit also can be built as Hachirokusu?
Not exactly. Because if you can take a Hecke orbit of anything, and that has nothing to do with hot locus. But oftentimes the cases we care about is the Hecke orbit of some component of the hot locus.
You have any other questions?
One more question, sorry. Yes, I mean, but I think that anyway, this kind of strategy also can be done for any surface with PG or one and whatever kind of Morales theorem is true.
Yes, yes, that's true. So it's stated for K3 is for completeness, for completeness, but the same theorem also holds for quite general surfaces with h equal to 0 equal to 1. I had a previous paper with Paul Hamaka and Xiaolei Zhao, which works out the Tate conjecture in that general. So then it just becomes a statement about orthogonal varieties themselves, which is known by this paper.
Okay, so if there's no questions, so we'll thank the speaker again for